Now let's see the Pmos common source amplifier. So for this, first we need to create the new circuit in the LT-Spice. So now we need to include the Pmos component from this toolbar menu. So we are using the monolithic MOSFET. So Pmos and click OK. So this is our Pmos. Then the first step is to name all these things, which is gate and which is drain and the source, so it will be easier. So always remember this is the gate, and in the PMOS the above one is the source. That is, it's exactly opposite of the NMOS. So now, yeah, this is the drain. And always remember this is the base for the monolithic transistor, and this we need to connect it to the source. So I'm taking the wire and I'm connecting from this to the source, and I need the two voltage sources, that is the VGD and the VDS. Okay, so this is for the input, and even I need to give the supply for this one, that is the VDS, and even I need the register. So just click on the R and get the register. The ID will flow from the source to the drain, and if you want to take the output, that is the voltage drop across this register, that's why we need this register. And now we need to connect these things using the wire. I need to connect this drain to this register, and okay, then this gate to this supply input supply. So always remember in PMOS that will be here is the P channel. So the gate has to be negative, because here the more electrons, then it will attract the more holes to the channel, and it increases the current flowing in this PMOS. So we need to give the negative supply for this gate. So for that we are making this as a negative supply. So we call this as a V D and S. Okay, so this is to be connected to the source, because in PMOS it is the opposite of the NMOS. So what we have to do now means the ID has to flow from source to drain, so the electrons will be from drain to source. So this drain part we need to connect it to the negative supply. So I need to connect from this resistor to my supply's negative. Then this positive has to be grounded. Okay, so here we need to make one ground, and here also we need to make one ground, or else we can connect from this to this source, and the source is anyway connected to this positive and it is connected to the ground. So let's connect it. Okay, this is to be connected in order to complete this circuit, and this one to the ground, because here we need the negative supply. And this also, even we can connect to the source, or we can just connect this to the ground, because these both are at the same potential or the same node. These two form the same node. Okay, now we need another thing, that is the model. So model for this PMOS, I'm going to this command spice directive and write dot model and PMOS and PMOS, and we need to specify the two parameters, that is the minimum of two parameters. So that is the KP. So KP equals to, it is 200 U, and another thing is the VDO, that is the cutoff or the initial threshold voltage for this PMOS. So below that voltage this PMOS is in the cutoff region, so this VTO is minus 0.6 volt. We need to have this directive here, spice directive. Now let's do the DC analysis for this circuit. That means we need to vary this VDS and even this. Okay, let's call this as a VDS. Okay, sorry, this is not the VDS, it is VGS. Okay, this has to be because it is connected to the ground and the source, so this has to be VG and VS, and this is connected in between the source and the drain, that's why it is VDS. Now in order to do the DC analysis, either we can go to here and we can write the spice directive, or simply go to this simulate and edit simulation command, and here we have this DC sweep, and I need to write VDS. I need to change this type is linear, and I need to sweep from 0 to 5 volt and the increment of 0.1 volt, and even I need to sweep this VGS because we need to know the circuit how it will going to act for different values of these things. So VGS, this has to be negative, so start value I'm just going to start it from 0 and to so we'll call this 2 volt, and increment is so this is not 2, this has to be minus 2, and here increment will be the minus 0.1. So that's it. Now we will have it here, and we can just make this register as a 0 for a time being, and we'll just check it how this circuit will going to simulate now. So it is giving error VGS. So instead of this V, we need to specify some parameters, or else we can just remove this, or else we need to specify some values, otherwise it will going to give us the error. Now there is no any error. If you look at the current here, then you can see this is the characteristics of the circuit. So here you can see the below value, that is in these regions, that is the cutoff region, and then comes this is the linear region, and here is the saturation region. Always remember the amplifier has to work in the saturation region. So we can just get these values from here. So I just need to click on this, and we can just get these for different values. Here you can see it is varying from 2.6, 2.8 like this. So our VDS, in order to be maintained in the saturation region, this has to be so we can see here this has to be this has to be around 1.4 volt or 1.6 volt. This has to be let's consider this 1.8 volt. So we need to have this as a 1.8 volt because it has to maintain in the saturation region. So this is the triode or the linear region, and this is the saturation region. So we need to, for the better amplification, we need to have this in the saturation region. So I'm keeping this as a 1.8 volt, and let's keep this register as a resistor value as a 2 kilo ohms. 2k. Then click OK, and this VGS, this has to be it has to be greater than the threshold voltage, that is the threshold voltage, that's minus 0.6. So we will just do this as a sine wave, so because this is our input. So we give our DC offset for this as a minus I'm giving this as minus 1.1 volt, and here I'll say 1 millivolt we have, and the frequency of 2 kilohertz. Then click OK. Now we need to just comment this DC sweep. I'm just commenting this, and we need to make the transient analysis. So for this one, the stop time is 10 milliseconds, and this is 0, then in the increment of the 10, and click OK. So now if I run the so this is now current we are seeing, but we need to see the output voltage, so I'm seeing just here. Okay, this is what the output voltage we are getting. I just forgot to add this length in the width. Let's say this is a 1 micro and this is a 100 micro. Okay, now if we simulate it, then we can see we're going to get this. Oh, there is no any gain in the circuit, because when we compare this input and the output, there is no any gain, much gain. So the input is also the 1 millivolt, output also 1 millivolt. So we can just change this to, okay, we will change this to a little bit less, like 0.8 volt we will do. Okay, now we will check this, and okay, so yeah, now we have, this is my input and this is our, okay, with our input and with our output. Let's see. So this is our input that is represented in this green color, and okay, I need to see my output. So okay, this is our output. So we can see our output is slightly amplified because our input is too less. We can just zoom like this. So here we can see our input. Okay, this is what our output is. So this is from 1 volt. So okay, 992 millivolt to something 1 volt. So yeah, this is amplified version. Because we can see here 992 milli to 1. This has a volt swing of around 8 millivolt swing. So 1 volt will become the 8 millivolt. Hence we can say this is the amplifier. It's amplifying, but the gain is very less. I think you understood these things. Thank you.